Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a very exponential, or should I say very exponential equation with complex numbers. If you're new to complex numbers, go ahead and check out my lecture videos where we go over basics of complex numbers, and anything you don't get, ask questions and make comments, subscribe, watch the videos, support the channel, all of that stuff, okay, so we can hit the algorithm. Now we have a very interesting problem where we kind of like have a tower, but that's not an infinite tower. I believe we've done an infinite tower problem before. Correct me if I'm wrong. If we haven't done one, we can do one. I have another channel that focuses on algebra, number theory, and trigonometry problems. Maybe that's where you came from. If you did, say hi. It's called Cyber Math, cyber with an S. All right? But this channel is all about complex numbers. The other channel is mainly about real numbers. And guess what? Yesterday, I just made a video on that channel. That's my very first channel. And I have two other channels, this one and the shorts channel, which is once a week for now. If you have any problem ideas, go ahead and let me know in the comment section down below. Great, let's get started. So we have this equation, e to the power z equals 1. And this could go on forever, hopefully, right? Or maybe you're going to have 10 of these. Well, the more you have, the merrier, right? The more the merrier. It doesn't always apply to math problems. But in this case, we have an interesting scenario. It's not like e to the z equals 1, right? Because that would mean z equals 0. What about e to the z equals 1? I think we've done this problem before. And would this mean e to the power z is equal to 0? Uh-oh, that's impossible even with complex numbers, because e to the power something can never be 0. Make sense? I hope it does. If not, let me know. But this problem, 0 is not the only way to do it. There's different ways to do it. We can apply the same scenario here with more steps. But the whole idea is the same. What is that whole idea? The idea is use Euler's polar form. Thanks to Euler, because he is the best, in my opinion. You could argue that. He gave us a beautiful formula. What is that? It's called e to the iz equals cosine theta plus I sine theta. I meant e to the I theta. Sorry, I don't know why I wrote z there. But of course, you could replace theta with z, definitely, right? But does that really give you anything about e to the z? Well, here's the thing. If you're able to write 1 in this form, suppose this is 1, if you can convert it to this form, then you can convert it to this form. Why? Because there's a direct relationship, and it's beautiful. You know why? It brings together trigonometry, imaginary numbers, arithmetic, exponentials, transcendental numbers, crazy stuff. There's nothing crazier than this, in my opinion. Correct me if I'm wrong. But this gives us the most beautiful equation. Anyways, I can't tell you enough about it. So let's get to work. So how do you write 1 like that? Well, the polar system is going to help us. We have a real axis, the imaginary axis. And if you have a number like z equals r times e to the I theta, where r is the modulus, the absolute value, then you can write it like this with an angle theta. And of course, r is the distance from 0, which is the absolute value of z, right? So you can absolutely do that. What about 1? Well, if you think about the coordinate plane, where does 1 appear, right? 1 is right here. I meant to use a different color. Guess what? I'm going to change it anyways. So this is 1 unit from 0. And guess what angle it's going to make? 0 radians, 0 degrees, or 2 pi if you make one rotation, or negative 2 pi, depending on how you look at it. But we can safely say that 1 can be written as e to the power 2 pi n I. It's I times theta, but this is your theta. Multiple of 2 pi, or multiples of 2 pi. By the way, n is an integer before I forget to tell you that, right? And did I say I squared is equal to negative 1? Hopefully I did. If not, I apologize. But 1 can be written like that. So that's a good thing, because we have a lot of e's, right? e to the z equals 1. But I'm going to replace 1 with e to the power 2 pi ni. What is n? N is an integer. We can specify and say, hey, I want n to be 0. In that case, we would have a very simple solution, because e to the z would be 0. But as you know, that's an interesting scenario, isn't it? Anyways, we can look at all these things, but let's go ahead and break it down. Now I have e's at the base and this stuff at the guitar. I mean, just joking. So that's our exponent, and this is our exponent. what does that mean? If you ln both sides natural logs, then you can kind of write this as e to the z equals 2 pi ni. By the way, you don't need to add anything to this because 2 pi ni basically will take care of all those rotations. Okay? Great. Now, we have another interesting scenario, right? Like I said earlier, if n is equal to 0, you're going to get e to the z equals 0. Is that going to give us a solution? Probably not. You know why? Because in order for e to something to be 0, the exponent needs to be negative infinity. But that's not a number. You can approach negative infinity. You can take the limit. Hey, this is not about limits. We're not taking limits or we're not doing calculus here. It's simple. Keep it simple. We're doing complex numbers, right? So this is not going to be good, which means n cannot be 0. So if n is different from 0, let's just take a positive n. How about n equals 1? Okay, great. This is going to give us an idea how to solve it. Obviously, I'm not going to go through all the n values, but at least this is going to give us something like this, which is easy to work with, right? Now, think about it this way. Can we write this in polar form, in exponential form? And the answer is yes. What is 2 pi? 6.28-ish, right? It's a positive number, positive multiple of I. Where does that number show up? That number is going to show up here because this is the imaginary axis, and anything that is a positive multiple of I is going to be here, which is going to be 2 pi units from 0, or the origin. And the angle it makes, because it has positive i's in it, is going to be pi over 2 radians. Beautiful. Then we can write this as 2 pi, which is r, times e to the I theta, which is pi over 2. But you got to remember, you always have to add 2 pi ki. In this case, I didn't want, I meant to say 2 pi k because I is already added. So when I use parentheses, I want to make the k different from n because they don't have to be the same. Okay? Great. So this is what? E to the z. We're not there yet, but we're getting closer. Now, here's my equation. And if I gave you this problem, if you want, go out and take a break, pause and take a breather, and then come back, because this is going to feel like, you're going to feel fresh, right? If you take a quick break, because this might be too much sometimes. Anyways, here's what we're going to do. We have e to the z, and we have something like this, right? Exponential. What we got to do now is to write this in exponential form. But how do you do that? That is interesting. Maybe we can do this. We can write this as e to the z equals 2 pi times cosine pi over 2 plus 2 pi k plus I sine pi over 2 plus 2 pi k. And again, this comes from the identity we talked about before. Remember Euler's formula. This gives you that. Now, what is good about writing it this way, though, right? And even simplify things, I'll take k equals 0. Again, when k does not equal 0, you can definitely handle that, right? Just think about it in general terms. But if I do that, my expression is going to be simplified, right? A tiny bit, which is actually really good, don't you think? Now, what is that supposed to mean? Well, we're going to do the natural log one more time. Wait a minute, did we really need to do this? Because what I'm thinking is, if I just natural log this, isn't that going to be easier? Absolutely. So let's go ahead and forget about it. You see, sometimes you don't necessarily use this right approach. First, you make mistakes, which is natural. That's why I'm not going to cut this part. And I changed my mind. I'm going to use something else, okay? And this part is, I think, gone right now. All right, great. So let's go ahead and take this. Natural log both sides. It's going to give us e to the z. When I natural log that, it's going to be ln of 2 pi, which is like a real valued ln, plus I times pi over 2 plus 2 pi k. Easy. Once you ln both sides, you'll get rid of some of the exponentials, not the whole thing, because we still have e to the z. All right. One more step. If we can natural log both sides, we should get the answer. But here's the thing. Can we write this in polar form, in exponential form? And the answer is yes, because think about it this way. Suppose this is equal to b. This is like ln 2 pi, and let's call this a. This is a plus bi. And guess what? A and b are both positive, of course, as long as k is positive, right? Because if k is negative, Houston, we have a problem. B is going to be negative. But if A is positive and B is negative, you're going to be in the fourth quadrant. So you kind of have to arrange the polar form accordingly. I'm going to show you this simple case because I'm lazy. Let's go ahead and go with A is positive, B is positive. In that case, here's what you're supposed to do. How do you turn A plus BI into the polar form? Here's what you do. First of all, you look at tangent theta, which is B over A, and make a graph and you'll see why. And then what you need to do is find R, which is the square root of A squared plus B squared. So in other words, this expression can be written as A plus BI, which is R times e to the I theta. But what is theta? If tangent theta is B over A and B are both positive, then theta would be arc tangent B over A, which is shown as tangent to the power negative 1 in the United States, which is very unfortunate. I think arc tangent is a much better expression for inverse tangent, okay? But this is what that's going to look like. So theta is going to be like this. And guess what? This is not z. This is e to the z. So you have to ln both sides one more time. Oh, man. This is crazy, isn't it? That's why I like this problem. But if you natural log both sides, things are actually going to be pretty easy to do because you're going to get something like this. Now the question is, what is B and what is A, right? Well, let's take a look. A is ln 2 pi, so let's go ahead and substitute that. Ln 2 pi squared plus B squared. And what is B? B is pi over 2 plus 2 pi k, pi over 2 plus 2 pi k, and I need to square that, plus I times arc tangent B over A, and remember, B is just going to be pi over 2 plus 2 pi k divided by ln of 2 pi. I forgot the parentheses. I hope you'll forgive me. Let's do it. And this would be the answer where k is an integer. I probably took n equals 1. That's why we got this. If I didn't, things would get more complicated. There are definitely much more cases depending on the values. But this gives you hopefully an idea about how to solve this problem. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe. Take care. Don't forget to check out Cyber Math and A plus BI. And bye-bye.